Welcome back to the COS 217 lecture. Today we're going to step back from the details and design decisions of the C programming language and turn to the other key focus of this first half of the semester. Programming tools and the programming maturity aspect that we're looking to develop the ability to be more than just casual hackers and more of structured engineering approaches to software design. So last week in Precept, you worked on a running example of a program to learn about multi-file C programs. This was version 3, just with the comments taken out so we can fit on the slides. As a quick reminder of the program, we had an interface file, intmath.h, that declared GCD and LCM both to be functions that return an int after taking two int parameters. The implementation of these functions is in intmath.c, where we pound include intmath.h using quotation marks rather than the angle brackets, since this is a local file and not part of the C standard library. Including it in the implementation allows us to type check the definitions of these functions against the declarations that we declared in the header file. Testintmath.c is the client program. It also pound includes intmath.h so that the compiler can check the calls of GCD and LCM versus the interface. Note that because both of these two C files pound include intmath.h, if we change intmath.h, effectively we have changed each of the two C files as well. This is because the first stage of the build process is going to be the preprocessor pulling the declarations into the C file from the .h file. So thinking about this, as we build our executable, changing intmath.h effectively changes all three of the files, so we must recompile both of the .c files and then reassemble and relink. But that would actually also be true if we touched any of the three, because it's all one command when we do our shortcut GCC 217 command all in one. That's okay here, it's two very small C files, but real-world projects have quite a few more. It's not unreasonable for there to be hundreds or thousands of .c and .h files in a project. As of this month, Bash has about 375 such files, and as of 2018, the Linux kernel consists of over 25,000 C files and over 20,000 header files. The Windows codebase as of 2017 is about 3.5 million files of all types. So with the large number of files and the potentially complicated dependency chains, even though this comic is a trope, it's true that there are projects where compilation of everything and linking of everything will take hours. Monolithic build processes that take into the hours would be a very challenging development environment, effectively returning to the bad old days of punch cards where basically everything was a batch job instead of an interactive login session. So as a first step to avoid this, in the real world, the build process is done in two levels, rather than with the all-in-one shortcut. Step 1 is to preprocess, compile, and assemble the .c files to generate .o files. And then step 2 is to link the .o files to generate the executable binary. What benefit does this give? Take a moment to think about it, and as a hint, consider that a key element of this scheme is that we retain the created .o files. Pause the video and take a minute to think about it. The key benefit is that if we build each .o file separately and keep them around, then we only have to rebuild things downstream directly from any change. So if we change intmath.c, that doesn't really in any way impact testintmath.o, so we don't have any new work to do there. We just rebuild intmath.o, and then relink our old testintmath.o and our new intmath.o into the new executable. As is, this saves 50% of the potential .o files from being rebuilt. But if your program is much wider with many .o files, this could be an even bigger win. So in this same program, let's go back and look at our original premise. We change intmath.h, which is effectively changing both of the C files. Even partial builds won't save us here. If interfaces are widely included, which is common, then changes to them have dramatic downstream effects. That's why we often emphasize thinking hard about your interfaces, which are much harder to change, versus your module implementations, which may not have as many levels of code depending on them. So this sounds nice in theory, but real talk, isn't it just easier to use the shortcut because you don't have to keep track of what has changed versus what hasn't? Well, it would be nice if there was a tool that used the dependency graphs we showed in the previous slides and automatically figured out which files needed to be rebuilt based on when they were last edited, perhaps. At least relative to the other items in the dependency graph. We'd totally use that, right? That would be great. Well, that's Make. It's a tool in which you specify the dependency graph in text, actually pretty close to the text format we had you use for the DFA in Assignment 1. And it analyzes your file's modification times and figures out which need to be rebuilt and which don't among the components of your program. I think it's a really great tool that everyone should use, but frankly, most terms, people say, I'll learn about it later. I'm going to just use the other things you've told me about using my history and Control R, and searching through it, it'll be fine. But after a while, you find that you do have a lot of builds, a lot of different build commands, and you do have other things that make it so this can be a nice tool. I encourage you to give it a chance. So, as a quick aside, obligatory Princeton content, Stu Feldman, class of 68, is the one who wrote the first version of Make. In the Unix tradition, he did it over a weekend because he was frustrated that things weren't working on the project, and he kept wasting time due to inefficient and ineffectual builds where things got updated and weren't rebuilt, or things weren't updated and yet were completely rebuilt. So he did this at Bell Labs, really in the nascent days of the Unix project. Stu Feldman's an interesting guy. You can see some small part of his resume there. A prolific career, including now even being board chair of the Center for Minorities and People with Disabilities in IT. So a really broad, not a traditional engineering approach to this either, especially for someone from, let's call it the previous generation. So the tool survives many iterations later in a modern GNU version. The command itself is quite simple in the common case. You invoke it with make and the name of one or more target files that you want to build. As an option, you can give the name of the Makefile, but if you don't, by default, the tool will look for files called Makefile or capitalized Makefile, and those are the two sort of default names that most people will use. I personally like capital Makefile just because the way that the ls command alphabetizes, it puts it earlier, but your choice in terms of the exact naming, except for assignments where we'll tell you exactly what you have to name it. So there are numerous other options to control, for example, what it prints out or what it does when it encounters an error, or what environment variables it looks at or doesn't look at. But for this class, we're mostly concerned just with the basic cases for targets and pseudotargets. So that's the command, but the real attention to detail comes in crafting the Makefile itself with those targets and pseudotargets. So the dependency graph in the Makefile is represented as a series of targets, a series of things you might want to build. Each target has 0 or more dependencies, aka prerequisites, which must exist before the target can be built, and then a command that will be run to build the target once the prerequisites are satisfied. The target will be rebuilt if it is older than some of its prerequisites. After all, if they've changed, it will probably have to change too. So this isn't just a matter of this doesn't exist, how to build it, but also there's the logic that the tool has of what do I need to rebuild based on what has changed in the system. So let's take a look at the Makefile for our running intmath example. Each of the 3 partial build steps in the tan boxes is represented as a command in the Makefile. So how do we build testintmath? It's the bottom GCC command, And where is that in the Makefile? It's the first target. The command is exactly what we see in the tan box, and the dependencies are the exact dependencies we see in the graph, the 2.0 files. But note that dependencies may be more than just the files mentioned in the compilation command. For example, we never include the header files in the compile command, but our premise in this entire time has been that we have dependencies on them. Recall, if intmath.h changes, that impacts both of the 2.c files in building their .os. So returning to our new partially built friend testintmath.o, how does it get to that partially built state? It's the tan box in the top left, which compiles it out of testintmath.c. But we know it also depends on intmath.h, so we need to make this explicit in the Makefiles prerequisite list. So let's look at this second rule. We also see something clever. The target of this rule is a prerequisite of a previous rule. We've said that the command gets executed if the prerequisites are met, but until now I've sort of elided over what happens when the prerequisite is not met. What happens is that it tries to make those prerequisites. Recursion is at the heart of make. So let's step through this process. We try to make the executable, which doesn't exist. So make checks on its prerequisites. The first doesn't exist, so we recur and make the prerequisite. You can see in the bottom of the window that the first compilation that happens in the command to build testintmath is the first prerequisite, testintmath.c being compiled into testintmath.o. So we then check, does intmath.h exist? It does, and now we can do that command. So having accomplished that, we check the box that testintmath.o is done, and now we can check on the second prerequisite. Does intmath.o exist? Again, it doesn't, so we're going to recur. We're going to check, is intmath.c, does it exist? It does. We'll check the second prerequisite for intmath.o, intmath.h, it also exists. And so now we're able to invoke the second command in the bottom box, gcc 217-c intmath.c, to build intmath.o. So we produce intmath.o, and at this point now we've satisfied both of the prerequisites for testintmath, and we can in fact produce testintmath. So now let's explore the partial builds in action. As we just saw, initially, all three of the GCC commands were executed. But now, after we've produced testintmath, if we touch intmath.c and remake, we only have to rebuild the portion that changed. Testintmath.o hasn't changed, so we don't rebuild it. You'll see here that there was no gcc 217-c testintmath.c resulting from the second make invocation. And if we do another make immediately, we'll see that nothing has changed, so there's no work to be done. We can also just do make here, and this shows that the default target is the first one in the file. We'll talk about the conventions of this in a bit, but first let's check on your understanding of the targets and dependencies. So pause the video here and consider this question about what files should be prerequisites for building 8.0. Certainly we need a.c, but a.c depends on a.h and c.h. And c.h recursively depends on d.h. So we need all of them, e. More generally, a proper dependency rule for any .o file is going to include prerequisites for the corresponding c file, but also the entire hierarchy of h files included from that c file. Here's another one. Again, pause the video and take a crack at this. Write down or otherwise give some explicit manifestation of your vote. Hold yourself accountable so that you can't just say, oh yeah, I knew that. because frankly, oh yeah, I knew that when reading the released answer key after bombing an exam is little consolation. So here, unlike before, we don't have a big chain of prerequisites. The executable lists only the 2.0 files as prerequisites. The 2.0 files, which will themselves be targets in the Makefile, at least usually, and then the Makefile, if that's the case, will do recursive descent to determine if D.H or C.H or A.H or A.C or B.C have changed, but it only relies directly on A.O and B.O for A. So our answer is A. More generally, an executable will depend only on .o files, not on .c files or header files. This maximizes partial builds and maximizes our use of the Makefile's recursive dependency checking and building. The next Makefile feature that we need to know about is pseudotargets, which are rules whose commands don't actually create a file with the target's name. That's why they're also called non-file targets. These are shortcuts that are idiomatic to trick Make into doing some work for us. Let's see how they work. We'll use the example make all in this version. So make observes that all doesn't exist. There's no file called all in the dependency. But it depends on testintmath, so that might or might not exist. So make will say, I'm going to recur and go make testintmath. Once testintmath exists and is up to date, all's prerequisites are satisfied. So make now builds all. But what's the command for that? There isn't one. And that's okay, because all of the Makefile commands have no post-condition check. There's no check to make sure that the file actually got created. There's only an exit status check, which says, did the command that I run fail? In this case, it didn't run a command, so it didn't fail. And it doesn't matter that the file called all wasn't created. So there's no file named all, there will never be a file named all, and so all will always continually cause Make to try to build its prerequisites. We just saw that the default target to build is the first one in the file, and so combining these two ideas, you'll often see that the first target in the file is the pseudo-target all, and typically its prerequisites will be all of the executables that the Makefile can produce. But another common alternative for the first target is make help or something like it that will just produce a usage message telling you what targets are available. That way, just typing make doesn't result in potentially a lengthy set of builds of building a whole lot of different commands. Other common pseudo-targets along with all are clean and clobber. And note that all, clean, clobber, help, these are just convention. They're typical names, but they aren't special. They're not keywords or standards. They're just descriptive. So looking at this clobber and clean command, pause the video and see if you can predict what clobber does step by step. So when we do make clobber, make observes that the clobber file doesn't exist, and so it has to be built. So make looks at its dependencies and sees that clean is a prerequisite for clobber. So make goes and says, well, I'm going to make clean, and I observe that the clean file doesn't exist. The clean file has no dependencies, so make moves immediately on to the command for clean. It issues the command rm-f testintmath and star.o. This deletes the executable binary file and all the .o files that made it up, and it returns success. It doesn't actually create a file called clean, but again, make doesn't check this. we pop back up to the initial dependency rule, clobber, and now, having satisfied its prerequisite clean, we build, supposedly, the clobber file by issuing the command rm-f star tilde and hashtag star hashtag. This deletes all of the special files left around by Emacs, the backup files, and the work in progress files. Again, it doesn't create an actual file name clobber. Make doesn't know or care. So again, here, we're tricking Make into doing our bidding. There's no file name clobber. There will never be a file name clobber. And so we can run make clobber over and over again to do this cleanup work for us. So let's add some pseudotargets to our Makefile and see what it looks like. We'll make the commonly used all pseudotarget to build our executable, and we'll put it as the first rule just so that running make will invoke it. We'll add a rule for clean, and that will remove the executable and the intermediate.o files like we saw. But note, we might not want to automatically put this .o file in the make clean unless we aren't going to run make clean very often. Because remember, partial builds are our friend at this point. And then one more rule for clobber just to clean up the junk files left over from our editing process like we saw in the previous slide. And this is version 2 of our Makefile. So non-file targets are used really heavily, particularly to automate or semi-automate repeated commands. As an example, make submit might run the submit command with all of the right required files. In this case, you could say, okay, I'm going to go to the assignment specification, copy down all of the things I have to submit, and then put it in the Makefile so I can just type make submit rather than trying to remember that set of 3 or 4 or 10 commands in a row. I could do make splint to run the commands, the splint command on all the appropriate files, or make critter to do a critter analysis on all of the appropriate files. Again, this is a nice handy shortcut rather than going back to the specification and trying to find, what was that command again? Similarly, I actually use this literally every time I upload a video. I do make publish that will push all of the appropriate PDFs to the web and name them the right thing and put them in the right folder and give them the right access rights so that they're visible on the course website. And then after we talk about testing, you'll see that make test is a common thing to run an entire regression suite automatically. So at this point, we have a nice automated build system that it can clean up after itself, and we could expand it to do some naturally nice things that we will often want to do with our source code. So next, we'll explore some advanced features of Makefiles. So in the continuing theme of exploring the C preprocessor's capabilities, you remember pound define? If you don't, you'll get a refresher soon when you tackle replace and write in assignment 2. Makefiles have a similar feature for creating variables that then get substituted in each time they appear within the rules. The syntax looks just like a C variable assignment. On the left is the variable name, on the right is the value assigned, in this case the value that will be replaced textually, with an equal sign in between. So then we can refer to the variables using the variable name in parens with a $sign before it. And this is a common way, using these macros, to have 2 versions of your program. For instance, for portability, for debugging, or to switch between a stable and a developmental version of your code. Though frankly, source control branching is probably better for the latter case. It's convenient because we can do it so that no matter how many different files in our code base we would have to change to make to say, oh, I want to change to the debugging version or the non-debugging version, we in fact will only have to change a single line in the single file, the Makefile itself, to swap between them. So here we have CC is GCC 217, the $M. The $sign here indicates a comment. So this is just saying, hey, this is our GCC 217 command, but all we have to do is take off this comment, and suddenly now it's GCC 217M, which is a version that we'll see later in the course where we're doing some memory tracking as we do dynamic memory. Similarly, Yak and Bison are the two standard tools. All of the GNU tools have punny names if there's some other standard tool. So Bison is a play on Yak, which Yak itself was a yet another compiler. Again, beyond the scope of what you need to know, but these are two tools that are equivalent and just one or the other will appear on any given machine. So it's convenient to make a makefile in which we can just swap between them depending on which machine we're on and what tool set it has available. So here's the third version of the code. Again, we establish a macro for using GCC 217 or GCC 217M. We also have several options for debugging, adding -G or not, so that we can enable debugging in GDB. -D is how we add an extra definition to the command line. So -D and debug is exactly like we had done #define and debug somewhere in our program. And we'll see what this actually means next week when we talk about testing strategies. And finally, -O is turning on optimization, and we'll see that in some detail later on in the course once we talk about assembly language. So I mentioned it briefly above, but the commands have to begin with a tab character. It feels weird and antiquated now, but because all editors these days don't actually use tabs for indenting, instead they replace them with spaces. But in a makefile, you have to have an actual tab character at the beginning of the command, the second line in each target command. This is weird, but editors know about makefiles, so it's okay. Emacs, for example, will put a tab when it's in makefile mode, and it automatically turns on makefile mode if the file name is lowercase or uppercase makefile. And if you ever wanted to create a makefile that was not that, you can do escape X makefile mode. Other editors can be similarly configured to treat makefiles as special based on either their name or some runtime configuration. Some other gotchas about makefiles. You have to make make actually do something. Lots of people will define an all and then think sort of as though it were a switch statement that we can have sort of a fall through. And so if all has no prerequisites and no command, your makefile will forever sit there saying there's nothing to be done for all. And similarly, every year I get somebody in office hours who says, "Hi, I don't understand why my makefile isn't doing anything." And what happens is that they remembered to write a clean or a clobber rule, but they put them as the first target. So typing make just removes all the intermediate files and resets the directory. And so they type make again, and it's a perfectly clean directory every single time. So if you're going to write all as your first rule, it needs to do something meaningful, and all or your actual target should be your first rule. And finally, makefiles are awesome because they can automate things, but automating things can be scary. So automating deleting files or other operations you can't undo, be careful with that. Commands like rm-f, where -f says, remove the file, don't ask me about it, and don't tell me if anything went wrong. Kind of scary to have that be the command that you're doing automatically based on a makefile that you think is right. All right, so thus far we've talked about how to write makefiles from scratch. Frankly, though, I'm pretty convinced that all of the makefiles in the existence, save the very first one, were started off by taking one that already existed, copying it, and editing it. And that's totally fine as a strategy when we ask you to write your own, so long as the one that you're taking and editing is one that we've given you. There are also automatic makefile generating tools that examine your source code and produce the dependency graph for you and then produce the makefile from that. That said, these tools are not fair game for this course. We do ask that you compose the makefiles yourself and not generate them automatically. So the last couple of slides today are dealing with some advanced features, just so you've seen them. You won't be expected to produce them, but familiarity could be advantageous when trying to read someone else's makefile, because I'm not sure what it is about makefiles. Maybe it's the terse nature of it, or maybe it's because nobody ever writes their own and they copy and paste other people's. People seem to use some really weird, terse, idiomatic stuff in makefiles. And indeed, Make has a whole bunch of variables that allow you to do pattern matching of files within your rules and refer to the targets or dependencies automatically or some subsets thereof. So in this first example, we had testintmath.o and intmath.o to the left of the -o, and instead we fill that in automatically with $caret, which we can see is all the dependencies. And then in the original command, we had testintmath to the right, but here we fill it in with $@, to say fill in the target in this place in the command. So this is pretty typical. It's nice when you're writing a rule and you say, I either don't want to repeat the text, or maybe if I start adding that to pattern matching, I want to use whatever the pattern was because I don't know what the actual files were. So in that sense, we can see the second example. We had two separate rules, one for testintmath.o and one for intmath.o, and we replaced it with a single rule that would use the $less than to say the first dependency of this rule, whatever it was. So this definitely isn't as readable because we have to figure out what pattern applies rather than looking for the exact target. If I go searching through my Makefile for testintmath.o, I'm not going to find it except in my as a prerequisite in my build command. Similarly, if I go looking for testintmath.c, I'm never going to find it in my Makefile. So again, possibly less readable, possibly more cryptic, but on the other hand, possibly more readable for a large program than 1,000 different .o file target definitions. So you win some, you lose some. There's definitely both pluses and minuses here. So going one step further than just pattern matching or making slightly terser commands, Make actually knows how to build C programs in the general case. So if you don't give it a command at all, but the target is a .o file, Make will happily use the default $cc variable as your compiler, and it will fill in x.c as the source code that it just assumes will make x.o. Similarly, it can make executables from .o files, and the implicit rules that use the given files for building, it's also cool, we'll also use them as dependencies for checking modification times. So using these implicit rules doesn't actually cost you anything from the other functionality that writing them out explicitly would. That said, personally, this is where I draw my own line. Executing commands that aren't written down somewhere, at least in a pattern, is one step too far for me, and I find this more confusing than it's worth. But it is a kind of cool thing to automate and make things sort of minimalist in your build scripts. So, nevertheless, here is a final look at the extreme limits where we could push our running example. So our .o files lose their commands, their rules lose their commands, and then, even furthermore, they lose their .c prerequisites. So testintmath.o gets made by a command we don't see out of just intmath.h as far as we can see. Because the Makefile knows that testintmath.c would be used to produce testintmath.o, and it knows that we would use GCC 217 in this case, the $cc command with a -c to go from a C to an O file. The same thing for intmath.o. And then for testintmath, we can see that we give it the two prerequisites of the two .o files, and it says, I can take it from here. If I'm given multiple .o files, I know that I will just put all of them on the line and invoke the linker with my -o and create the final. And so this is actually the final version of our Makefile, in which we had a whole bunch of lines that are now reduced to 3. We're left with 3 very terse lines, a partial list of dependencies, and that's it. And Make will happily figure this out, but the poor soul who takes over your code, this project from you, will they ever be able to update your Makefile without having, or update your program in general, without having to throw out your Makefile and start from scratch? I'm kind of dubious on that. And as long as we're talking about this, though, one more final gotcha here. In case you were planning to go wild with the implicit rules, again, I beg you not to for anything that anyone might read. And notably, your assignments will ask that you use explicit rules, just so that we can be sure you've got the basics down. But one last gotcha when you're using the implicit rules is the naming has to match. The Make program can guess a lot on pattern matching, but if none of the names match, it doesn't know what to do. All right, so we've still just barely scratched the surface on Make. The King book has a good section on the tool, and then there's the man pages, of course. And if that's still not enough for you, the link here on the screen is the full GNU documentation. That's about 140 pages. It includes tons of examples, some common use cases, some frankly bizarre use cases that I don't know why anybody ever thought of, much less wrote down, and tons more. So I do encourage you to experiment with it. I truly hope that you'll become a convert, that Make is totally the right way to build software, as opposed to typing out the build command every single time, or even versus typing out the build command once, then using Control-R forever. So next time we'll come back to new features in the C language, including dynamic memory that we've been talking about as leading examples of we'll talk about it soon, we'll talk about it soon, we'll talk about it soon. Now is finally the time, so get hyped.